Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
Now, the one thing that we haven't done in this discussion is to talk about nominality. But before I talk about nominality, let me just stop here and see if there are any questions about what I've said.
Greg, that was a great explanation of what correct by construction is. So thank you on that.
Cool. I appreciate. I'm glad to help. So you know, the important thing is that we're in terms of the development methodology of RChain, we want to get Golang to the point where user contracts can be correct by construction. So that plugs the hole that any smart contracting system has, right? So any smart contracting blockchain platform has this massive security hole in it. As long as it allows for user-defined smart contracts, it is going to have this big old hole because they're code auditing does not catch serious bugs. And the DAO is a great example. The parity wallet error is a great example. And they will continue to happen over and over and over again until you can have some kind of decent correct by construction methodology. So if you wanted to hint, Christian, if you wanted to say what is the cream, what is the most disruptive feature of RChain, it's this feature that we can plug the hole, the security hole opened by smart contracts, right? So lots and lots of blockchains are going to ultimately get to high TPS numbers. Now, right now, most of them are getting high TPS numbers by sacrificing decentralization. So EOS sacrifices decentralization. Many of these will not have the trust model that Bitcoin has. So they'll advertise these numbers, but the fine print is you don't have decentralization, right? And in that case, who cares if it's a blockchain? Why not just use SQL? Why not just use Oracle or SQL Server or any one of those? Because ultimately your solution will be much faster using those much more hardened technologies, right? And also you'll have a much broader development base and a lot of code that you can reuse and yada, yada, yada. So if you're sacrificing decentralization, it's not a blockchain or it's not a valuable blockchain, right? You're just ticking off a checkbox. You're not actually doing the real thing. And it's much better in that situation to use these hardened, mature software tools, especially if you're doing anything mission critical like, you know, high dollar finance or tracking of mission critical resources or anything like that. Right? So you can't sacrifice decentralization and still have any rights to call yourself a blockchain. But eventually there will be decentralized. So remember that there are an infinite number of these economically secured leaderless distributed consensus algorithms. Infinity is a big, large number. So since there are so many of them, eventually there will be blockchains that have consensus algorithms that allow them, like RChain, to have high TPS. Once you have high TPS, now you have this glaring, gaping security hole if you allow for smart contracts. If you're a payments network, it doesn't matter. right? If it's literally just pushing one tokens from one side to the other, and the tokens are fixed, and there's no tweaking of behavior, doesn't matter at all, right? You can just build a better PayPal. So a decentralized PayPal clearly has value. There's no question about that. But if you want to do something more, if you want to do something more than PayPal, a decentralized payments network, if you want to be able to build real applications on top of the platform. So, and in particular, the issue is, if you look over the last 20 years of internet applications, what are the major applications? Let's think about them. Gmail, Google Maps, Facebook, Spotify, right? That's just a handful of many, many, many of them, right? So PayPal as an instance is a very tiny fraction of what's really going on. What's really going on is the movement of digital assets, right? Movement of tokens is a tiny, tiny fraction. If you look at internet traffic, the movement of tokens is a tiny fraction of internet traffic. Over the last 20 years, it's all been about the data. So if you build a network that is optimized for payments, it will not scale to data. So that's your next requirement. You need to have a network that handles data. That means smart contracting. Once you have smart contracting, you have a major security hole. What is that security hole? Users can write really bad contracts, like the DAO contract. Now, if you're running at 40,000, if you're running at Visa speeds, 40,000 transactions per second, and you have a really bad user contract, that can bring the entire network down. And the usual security issues, security workarounds, like running things in sandboxes, don't work. The whole point of this network is that the smart contracts interact with other smart contracts. If you sandbox it, now you have eliminated its economic viability. So that kind of security doesn't work. We need a new approach to security. That's where the correct by construction stuff comes in. So you plug that hole with correct by construction. And that is the disruptive feature of RChain. Now, the interesting point is that it's more disruptive than just plugging a security hole. And that's because if you squint, this type system becomes a query language. So you have some resource of these programs, these behaviors, right? So from our point of view, the programs are just these terms like C and K, and those terms are behaviors, right? They could be programs like you store on GitHub, but they could also be other things. For example, models of cell signaling that are currently stored in boutique databases all around the biology community. They could be other kinds of things like geometric data. So they could be terms that represent geometric information, like the kinds of things that Boeing uses to model its airplanes, or that Toyota uses to model its cars. All of those kinds of terms are stored in a database, but searching those kinds of data. So GitHub is one example. These boutique biological databases are another example. The geometric information that Boeing and Toyota and other things use, those are all examples of what I'm talking about. Searching those kinds of databases on the basis of behavior together with structure is impossible today. It can't be done. So let's sink that in. Let that sink in. You can't do that today. That means that searching GitHub is reduced to tagging things with meta tags, metadata, or social searches. And that can only get you so far. It will not get you all the way. What these richer type systems do is they allow you to form a query language. So you can now go query for things in your database, which are just terms in a programming language that satisfy a particular specification. And now your specification can be fairly rich, fairly detailed, without giving away the farm. If the specification is just a full-on program, then you're out of luck. The search may take forever. At least you have a search now, but it may take forever. But as long as you keep your specifications dialed back in terms of expressiveness, then you can go, then your searches will complete in finite time, and you'll get very useful answers. A really good example of this is Kairos in his spatial logic for spatial and behavioral observations in the logic for the pi calculus. In that paper, he identifies a class of terminating, of processes, and and a limit on the logic where that check is terminating, and it's quite rich. You can do quite a lot with that. So you can build up hierarchies, and if you want to have your specifications be so rich that they're effectively programs, then you can also rate limit it using the same strategy we've used here. You put a resource on it. So it will keep searching as long as you're willing to spend. So this gives you a new approach to many, 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 many things. So for example, a kind of query language is you can not a kind of query language, but a kind of query. So you can formulate queries of the following form for the boutique biological databases. Find me all the small molecules which, when introduced into a cell signaling pathway in this concentration, prevent it from reaching this state. Right? So that query is medicine. That query is a cure. You're talking about introducing a drug into a cell pathway to prevent from reaching a certain state. Let me give you an example of such. So in his book Lifespan, David Sinclair, who is a preeminent Harvard medical researcher, has identified what he believes is the single source of aging. It has to do with epigenetic errors, and the cure is essentially error correction. So let me give you an example of one such pathway. So in this pathway, the sirtuins, so there are sirtuin genes, gene structures in homologous sirtuin gene structures in yeast, worms, mice, and humans. And what the sirtuins do is they have two jobs. Job number one is they repair damaged DNA. Job number two is they prevent the cell from duplicating. So essentially, the DNA breaks all the time. It happens all the time under normal operating conditions in the world. And you need some mechanism by which you repair it. So that's the job of the sirtuins. And also, you don't want the cell to be replicating or duplicating in the case that the DNA is damaged, because you'll end up with two copies of a cell with damaged DNA. Or maybe one copy has some of the DNA and the other copy has some other DNA. That's aging. Replication of damaged cells. That's aging, according to Sinclair. So now we have a clear pathway. And the question is, find me all the small molecules that when you introduce it into that pathway, you don't get this to happen. So an example of a solution to that query would be NAD. What NAD does is it provides additional fuel for the sirtuins, so that if they are overwhelmed doing damage, they still have enough juice, so to speak, to prevent the cell from duplicating. So that's an example of a solution to such a query. Now, my argument is that if you have a stochastic version of this type system, you can write that down, and it's quite possible that the query system would find NAD as a solution. So, and just to give one more example of what I'm talking about, imagine that you want to reason about pathways for a self-driving car. So you want to represent the pathways in some kind of algebraic data structure. So it turns out that in the last 20 years, people have been vigorously investigating an algebraic data structure called the Clifford algebras, because they have significant advantages for reasoning about geometry. Clifford algebras can be run through this very same algorithm, just like everything else that, just like the pi calculus or even vector spaces. We can run these algebraic data structures through this process and get a query language, but now your queries are asking questions about geometry. And you can use those queries to reason about paths in space. So you can use this to address, for example, navigation systems for self-driving cars. That's just, so I've now given you two far-ranging examples of what you can do with this kind of system, right? So the existing behavioral type systems for Rolang, which are derived from this process that I've talked about today, allow us to plug a major security hole that all the other blockchains suffer. And but even if someone stumbles on a very specific type system that does the trick for their blockchain, for their high TPS blockchain, where the bar is already so high, there's no one there. But even if a competitor or a cooperator were to do that, they still don't have the power of this algorithm, because this algorithm affects everything we do. It affects how we build buildings, how we build cars and airplanes. It affects how we do medicine. It affects everything. That's the point. If we get this algorithm rich enough, you can use it as a query language for a huge range of behavior. That's the truly disruptive capability of RChain. Does that make sense?
Yeah, it makes perfect sense.
Okay, so this is probably the 100th time that I have made these comments.
The reason why it doesn't click, Greg, is because I'm not a programmer. Now it clicks because you're doing trust at scale with the security, and then you're adding programs on top of that, and that's where it's disconnected from me because I'm not a programmer. So the two examples you just laid out, the more examples that we get that are high dollar value, especially in the financial industry, it's going to be a lot easier for me to wrap my head around this. But for everything you just said, this is going to make total sense for programmers, right? Because
just think about it as it gives you a query mechanism for a range of behaviors. Like right now, we do not have query mechanisms for rich behavior coupled with rich structure. That doesn't exist. This gives you a query mechanism for rich behavior coupled with rich structure. And you can think about the design of you think about the design of RChain as effectively iterating this. So if you look at our development path, RSpace is a new storage mechanism, right? So it's a key value database with a very important twist. Some of the values that we store are programs, they're continuations. So this is a delta from the Lynda tuple space. It's a delta from all the tuple space models. You get to store data and programs, and they're related by a constraint, which is at a particular name, at a particular key in the database. You either get data or you get program, but not both. Right? That's a integrity constraint of that data source. Right? So we built a new kind of database, and then on top of that database, you can view Rolang as, guess what, a new query language. So Rolang is the analog of SQL when looked at from the lens of database theory. The big difference is that unlike SQL, Rolang is Turing complete, but its semantics relative to the data store is perfect. They are in lockstep. There is no real difference between Rolang and the data store. That's why Rolang is, that's the essential correct by construction aspect. We have, you can think of the data store as being extracted from Rolang, or you can think of Rolang as being extracted from the data store. There's no delta between those two semantics. And that's why it's correct. You can't get a disconnect between Rolang and RSpace, at least in principle. In practice, because we don't have special tools that are checking things, we can get disconnects. But at least at the design level, there is no way that there's a disconnect. And then so Rolang is a query language for that store. And then these types become query languages for things above that, at the next level up. So essentially we're iterating that. And now if you look carefully at the development path of RChain. So first we built the data store, then we built the query engine, then we built, so essentially what you had was a Rolang interpreter. Then we built a communication mechanism, that's the comms layer, so that different Rolang interpreters could talk to each other. And then we added in Casper, and what that does is that makes sure that all of the different copies of this Rolang interpreter, which is a query language for the data store, that they are in lockstep with each other, right? So that if one copy does something, the other copy does the same thing, right? They're all in agreement. Casper puts in a consensus about that. So now you go from a distributed data store to a fault-tolerant distributed data store, because if any one copy fails, the others can take on the job. But that isn't resource constrained. So that computer, someone can put in a Rolang program that eats up all the network resources, right? So that's no good. And then the final piece that we just added, that's what testnet 3 is, we add cost accounting. And cost accounting basically makes each step in executing the Rolang program cost you some rev. And any storage that you do costs you some rev. Right? So that limits, so the only way that someone could eat up all the resources on the network is if they had unbounded amounts of rev. So that's not going to happen. And so you get the, so that's the economic security, right? The system is secured from those kinds of DOS attacks by this economic limiter. So that's the history of the development and how it relates to all of these different pieces, right? Essentially, we're just iterating a notion of building query languages because that's what people want to do, right? They want to store stuff and get it back. And we're adding different levels of semantics each time. So the first time, we're adding this capability to store data and program, and then building the semantics around that. And the next time we want to be able to reflectively introspect about the behavior of programs, and that's the type level query language. So that's how that's kind of the onion view of RChain. Hopefully that makes sense.
Yeah, it makes perfect sense. It's weaved together, and it's very, very difficult to understand from the outside if you're not a programmer. But that explanation, Greg, helps enormously.
Cool.
Yeah.
Cool. Good. Well, I'm glad. Any other comments from anyone else? Questions?
Yeah, this is awesome. Can you say how this K will look like in Roland?
Yeah. So K is par in Roland.
K is par.
Yeah. So you take you take the par of a for comprehension and an output, right? And that produces a term. And the rewrite rule is the com rule.
I'm having difficulty to distinguish par and the com rule.
Oh, well, par forms the term. So here, let me do it over here. So remember, K takes two terms, right? A T and a U.
Yeah.
So here's my T for Y from X to P. So that's my T. And it's a lowercase t, not an uppercase t. And my U, let's say, is on X spend Q. Okay?
Yep.
And now my K is T par U, which is the same as okay? That's just a term,
Yep.
right?
Yep.
And now the com rule says that that term can evaluate to P, in which we have an at Q for a Y. So
I see. So K only holds the term. It
K,
doesn't mean reduction.
That's right. K is equal to this, which is equal to that. Yes, and that's the trick, right? And then the fact, and then so just to be super clear, I'll make a copy of this. So then our rewrite rule row, go grab that. Okay, there's row. Okay, so now I have instantiated this for you for row calculus. Right. Everything that is done abstractly here, I've now specialized to row.
I see. So in K, it will never happen that some kind of reduction, right?
That's correct, and the reason is because we start with ordinary row calculus, right? And it doesn't need any resource R. And then we turn it into a theory where you don't get to do your rewrite rule unless you have an R. That's rev. That's your token.
Okay. I see.
So this com rule, so in particular, so we start with a theory like this, right? That's our theory. And then we make a new theory that says, oh, by the way, you can't do this. You have to have one of these in the mix.
Oh, so in plain row, K and row is the same, right? Because we don't have
That's right.
the
That's
catalyst.
right.
Oh, okay.
In ordinary row, this goes through. But in the new theory, you can't do a reduction unless you have an R.
I see.
And now, so now that the cool thing is that this K now becomes a kind of tensor. You have all that you need to do a computation, but you don't have the resource, right? So it is literally a reflection, and at the same time, it's a form of tensor.
I see.
So this is yeah, and yeah. So this
So,
is
for a marketing buzzword, what would this be? Like trusted computation at scale, or what? Like,
I
it's
don't
hard
know
to
yet.
package all this into like this is what RChain is in three, four words, right?
Yeah, let me think about it. I'll come up with some marketing language. But notice that that this whole approach, I believe, I'm going to have to do some work, but I think that this does better than snarks. And there's a reason, right? So my program extraction from my types gives me a way to just do. Someone is chatting. Anyway, yeah, I think that this allows us to do snarks. So, but I have a lot of work to do. So essentially, so what I've been telling the dev team, just to round out this thought, and then I've got to jump off. We don't have dev stand up today because it's a holiday, but I still need to take my dog out for a walk. Okay, so the idea is that right now, when a block is proposed by a validator, the validator has already run the COM rule and possibly several COM rules. And the other validators, their jobs are to check that running that collection of COM events actually will get you to the state that the proposing validator claims. So that's the sort of cryptographic security. So now, instead of the rerunning the program, what if we just constructed a proof that you could get from the state to the other state? And the way we constructed that proof is by starting from the state and running the proof backwards. So essentially doing a standard kind of theorem proving trick, using resolution techniques to prove that, you know, from the starting state we could get to this state without having to run the program. Then that would dramatically speed up what RChain does today, because replay takes more time than play, because it has to check some additional constraints about ordering that are in that the play doesn't have to do. The play just, you know, like, is there a match? Okay, you know, so if you look here, the play just says, is there a match? Okay, there is. I'm picking that one. Now, there might be a bunch of races, right? But it just picks one of the races based on the stake weights. But but the replay has to not only see that there's a match, but also make sure that it's the match that happened in play. So that's extra computation. If you could avoid that and just construct a proof without having to do the full replay, then it is possible. Again, there's a lot of work to be done to verify this, but it is possible that this is much faster than the way we're doing it today. And if we can do that, if we have this proof construction, then yeah, it's effective. It's effectively like snarks, right? So there are a wide range of applications. Basically, wherever you're seeing snarks being used, this is a place where you could substitute this in for snarks, and it allows us to handle concurrency and a bunch of other stuff. Anyway, go ahead.
This will probably be more performant than snarks, right?
By a lot. By considerably more performant, yeah.
This also sounds very like program synthesis. When we go backwards, and is there a connection?
That's exactly right. Yeah. That's exactly.
This is very interesting.
Yeah. So anyway, there's lots of work to be done still, but this is the whole point of the and this is why Ladle is so critical to RChain, because it's much deeper than just the behavioral types for Roland. It widens out the scope, so RChain can apply to many more things. And again, the reason we want this widened scope of applicability is because we have to change the manufacturing infrastructure. Right? Like, as an example, you don't want, if you could consult the database instead of running a bunch of chemical tests, that would be potentially far superior, because it would have much lower environmental impact. That's just one example of, of many examples where having a system like this would make it possible to dramatically impact the manufacturing infrastructure. Anyway, I've chatted forever and ever. Thank you so much for your time and your patience.
Thank you, Greg. This is exciting.
I'm glad. All right. Talk to you guys soon.